Hey guys, Kyle at MyersMathematics.com. Today we're going to talk about factoring. So, what I want to cover in this video is not a bunch of worked examples. I'm actually going to do a series of videos on worked examples of factoring. So there will be plenty of practice there. What I want to do here is I want to break down what factoring is, and I'll put a few, maybe like one example of each if I need to. But the idea, the goal here is to talk about what factoring is. So what is it? And then what are all the different types? What are the types? All right, so that's the goal here. So factoring is pretty much exactly what it sounds like, or maybe it's not. So you've probably been thinking of factoring as, you might have an example like this. So let's say you have x squared plus 4x plus 4, right? So you're probably thinking of something like this. So let me change over, use green here. So you're thinking this maybe, especially if you're in a section on factoring, then you guys are doing something like this maybe, where you have to maybe break this down and find out what that is. That's 2 and 2. Oh, hey, look, 2 plus 2 is also 4. All right, so then I do this. Oh, cool, look at that. All right, so that's factoring for sure. But that's not the only kind of factoring. There's a bunch of other different kinds of factorings. And you're probably thinking of all the different kinds of factorings you know about right now. But what if I told you that this was factoring? What if I said this was factoring, 24? Oh, hey, look at that, 6 times 4. Oh, okay, 3 times 2. Oh, 2 and 2. Oh, look at that. Right, so prime factorization trees, maybe? Prime factors. Right, I'm putting this in green because it's an example here. It'll be a theme that I use. I use green for examples. Yeah, prime factors. Look at that. So there's a lot of different ways you can factor in factors. Let's kind of define factors here. So let me insert a text box. Insert. And I'll just write it in here. So factoring. Let me change my pen here. Here we go. And try to get it to work here. There we go. So if we have factoring is when you find 2 or more numbers that multiply to another. All right, so this would be like the technical definition here. So let me blow that up a little bit. Make that a little bigger. All right. Factoring is when you find 2 or more numbers that multiply to another. So this is why this is factoring. 3 times 2 times 2 times 2 is 24. Boom. If you were to multiply all that out, you'd get 24. Well, hey, look at that. 2 or more numbers. That's definitely more than 2 numbers. Or this example. This is 2 things, right? 2 or 4 numbers. I should add to this definition 2 or more numbers or terms. As it gets more complicated, you end up multiplying terms. So this is a term. This is, or I should say, expressions. Right? So we have a binomial expression. 2 things here, 2 terms. And we're multiplying them. There's actually 2 of the same thing. So this is actually completing the square. But that's a whole other thing. So here we have 2 factors. Those are factors. These are factors. All this is factors. And there's a bunch of different ways to factor. So let's get into the steps. Like if I want to factor something, what is like the process that works for everything. That's what I love doing in my tutoring sessions, is showing what's the process that works for everything. If I come across anything to do with factoring, I want a method to solve every factoring problem ever. So here it is. Here's the steps. All right, steps, and this is going to solve every factoring problem ever. Solve every, sorry, that's a little sloppy, factoring problem. Solve every factoring problem ever. Here we go. So, step 1. And you're going to notice there's actually only, spoiler alert, there's only 2 steps. Because the second step is the more involved one. The first step is sort of like a precursor. So actually, step 1 is more like a precursor step, but I like to call it step 1. So step 1, look for a GCF. Look for a GCF. And if that term doesn't sound familiar, it stands for greatest. It stands for greatest common factor. All right. So what is that? What does that mean? If I have, here's an example, right? My green, for example, 2x plus 6. So if I have 2x plus 6, the common factor, they have a common factor of 1. Everything has a common factor of 1. So I could technically divide them both by 1 and factor out a 1. But that would be dumb, because it wouldn't really do anything for me. But they have a greatest common factor of 2. They both divide by 2. So if I divide them by 2, so if I divide them by 2, right? So it's like 2 over 2, so that's just x, and then 6 over 2 is 3. Now I've taken out the greatest common factor, and I'm done. There's nothing else I can do. X plus 3 is not, you can't continue to factor that even more. It's pretty basic. X plus 3 is pretty simple already. So that's it. We're done. So we actually just factored, right? So step 1, you're here, and we're done, right? So sometimes it's that easy, and then other times it's not. That brings us to step 2. Right? So that brings us to step 2. Step 2 is a big it depends. Not to be confused with the underwear. It depends. Okay, so this depends on, how many terms you have. How many terms? Okay, so then we're going to have a bunch of subsections here. So let's start with the first one. If we have one term, or actually, you know what? Let me use a little bit more proper labeling here. Let's use A. Use A here. Use a number, then I use a letter. A, 1 term. And you're probably thinking like, what? 1 term? I don't even factor it if it's 1 term. You can. I just did. Look at this. This is 1 term. Right? This is 1 term, and I factored it. Right? It's 3 times 2 times 2 times 2. And technically, that's factoring. Right? Factoring is, remember, when you find 2 or more numbers that multiply to another. That's all we're trying to do here. So for instance, if I have 1 term, it could be 3x. Right? Well, 3x would be 3 times x. Okay, that's a pretty basic example. And then, of course, factor trees. Right? So 1 term, something like this, or a factor tree. Let me put that, switch back to blue, or a factor tree. So factor trees are the most, common example of that. Split this up here. So a factor tree. So I'll put the 24 here. Actually, no, let's use a different number. Let's not be so boring. Use a different number. Give me a number between 1 and 100. Oh, 80? Oh, good choice. All right, so then we have 8 times 10. 8 is 4 times 2. Shocker. 10 is 5 times 2. Oh, not done. There we go. All done. So if I wanted to factor this, I could say 8 times 10. That would technically be factoring, right? 8 times 10, those are factors of 80. And then you can keep going, 2 times 4 times 5 times 2. Or if you wanted to use all the prime factors, I would do 2 times 2 times 2 times 5 times 2. And it doesn't matter what order you multiply them in, because it's multiplying. That's another video for another time. So then, let's go on to the next one. All right, so that was it. That's it. One term. You can factor tree it. You can, break it down like this, but that's pretty much all you can do. It's baby stuff. Baby stuff. All right, so now let's ramp it up a little bit. And you'll notice that as we have more terms, it becomes more complicated. That's kind of how it works. So oh, goodness gracious. I can math, but I can't English. 2 terms. So if I have 2 terms, what does that look like? Oh, by the way, binomial. Binomial. Look at that. 1 term, aka monomial. Like that nasty disease you don't want to get. All right, so if I have a binomial, then there's a couple options. There's actually a lot more options than I would like to cover here. There's mini option 1. Difference of squares. Difference of squares. All right, difference of squares. So let's do an example. So like I said, I'm not going to work out a bunch of examples, but I feel like instead of defining each one and giving you some sort of magic formula, I think it makes more sense to work out an example. And in the future, I'll show you more examples and more worked out examples for especially the more complicated things like the trinomials and my methods that I've developed or begged, borrowed, and stole. Maybe not begged. It just kind of sounds good when you say them all together. But anyways, difference of squares. Yeah, x. Let's say x. X is the variable that everybody uses ever. Let's square it. Right? We have squares. We need to have square numbers here. So 1, 4, 9. Oh, let's use 16. Let's do that. All right. So difference of squares. This is a difference of squares. So squares, and squares. My 2 squares right here. Boom. 2 squares. And there's a difference, meaning subtraction. All right, so this I can factor. And here's what I do. All right, so I'm going to do x squared. Let me write it again. What? You can't do that. Well, this is not pure math here. I'm just kind of square rooting this and square rooting this individually. I know this is not proper format here, but hang with me. I'm going to do this, and I'm going to do this. And there we go. We're done. All right, so why did I do a plus and a minus? Because if I were to FOIL it back out, right, so FOIL, right, so FOIL. Oh, let me use a different color because that is not the right color for that. It's a different color over here. Let's use a pencil. All right, so recall. So recall over here. FOIL, F-O-I-L. First is the worst. Outers, inner, last. Right? First, outer, inner, last. So if I FOIL it back out, if I were to FOIL this back out, I would get x squared minus 16. And you can pause this video if you want and check it. I'm not going to multiply it back out, but if you want to pause it and check it, go for it. It's gonna cancel the middle terms, and you're going to get x squared minus 16. So it works. Trust me. You got these 2 things right here, which, by the way, are called. These are actually called. These 2 things right here. They're called conjugates. Called conjugates, which is a fancy word for it has the same terms, right? So same x, same 4, but opposite sign in between them, right? So the second term is opposite, but it makes more sense, I think, to just say, hey, it's the same 2 things, just put a different sign in between them. And then the magic math thing for that is called conjugates. Why do we use fancy math terms? I don't know. People just come up with fancy math terms. I didn't make this stuff, right? Jesus did. And then mathematicians decided what to call it later on, because, I guess we get the naming power. Still Still getting the power of naming things that already exist. All right, so difference of squares. Boom, there it is. 2. All right, this is the only other one. This one's a little bit more complicated, and you're not going to see it that often in Algebra 1, especially. Maybe in Algebra 2, you might see it a few times. But, you know, between Algebra 1 and Geometry and Algebra 2, you'll maybe see this a few times. So I'm going to go ahead and throw this in there. Sum, meaning plus, right? Meaning plus. Or difference. A sum or a difference, which is minus. Might as well put that here as well. Right? Sum or difference of cubes. Of cubes. So then, all right, sum or a difference of cubes. Let's do an example. X cubed, right? It's a cube. Let's do plus this time. Right? So last time we did minus because we had to. So let's do plus because we can. Plus 8. All right, 8 is a cube number because it's 2 times 2 times 2. Check my math if you want. So what we're going to do is we're going to take the cube root. All right, I'll do a little bit more proper notation on this one. All right, cube each one individually. So it's x plus 2. All right, done. Just kidding. Okay, so what we're going to do is x plus 2. Then we have x squared. All right, so you square the first thing. Square the first thing, then you multiply them by each other. All right, so 2 times x, 2 times x. Oh, and this is minus, by the way. Whatever this sign is the opposite. So 2x, and then square this next. So square the first thing, multiply them by each other, and square the last thing. Plus 4. All right, this is always plus because whatever this sign is going to be multiplied by this. So if this is plus, it's not going to change the sign. That's the reasoning behind that. This is minus for the same reason that these guys here are opposite signs. You want stuff to cancel. So that's the reasoning for that. I'm not going to get into like all the reasons why the signs have to be the way they are. You can play around with the numbers if you want, but that's basically how it works. So let me use a slightly different shade of green actually into another quick example. So here's what it would look like. I'll go ahead and give you the opposite real quick. So if I did minus, this is what it would look like. I have x minus 2, still be x squared, but then it'd be plus 2x plus 4, right? Only thing that changes is this sign right here in this grouping of parentheses, right? So this sign and this sign here, right? I'll circle it instead because that's going to look like I'm trying to change the sign. So these two signs are the only ones that change in these parentheses. So in this parenthesis and the other one. So those are the only two signs that change. And then of course in this first parentheses here as well. All right. So that was not all the things. All right. So we're on B here, 2 terms. If we have 2 terms, there's only 2 things, at least that I'm going to talk about here. Pretty much only 2 things that you're ever going to see. Are difference of squares and a sum or difference of cubes. And this one, this sum or difference of cubes here, oh, let me not circle that. Ha, just kidding. That one's going to be not as seen, right? So let's go to the big dog, the trinomials. And they're actually not the biggest one, but probably the meanest, I guess, the one that you'll probably see the most. Trinomials. Right? Actually, I just put that, as everybody normally sees them as trinomials. You can also call them, you can just say it 3 terms. 3 terms. Trinomials is usually what you call them. Or quadratics. You can also call them quadratics. Quadratics. I like to call them quads. Quadratics. Right? I like to call them quads. I don't work out, but I like to call them quads. I don't know why. So the most basic example I'm going to call the basic example because I'm really original. Let's call it classic. Yeah, like Coke. It's like it's not called original, it's called classic because that sounds better. That's classic. Classic factoring. So I actually already did an example of this, but I'll do another one. And we're going to let's do x squared. Let's do minus this time. Why not? Do minus 5x plus 4. Hey, look at that. I did plus 4 again. So we want two factors of 4 that give me 5 when I add or subtract. In this case, I'm going to be adding because this is plus. I'll have a whole nother video for why we do all that. But anyways, I could do 2 and 2, but if I added 2 and 2, I'd get 4. And I don't want 4, I want 5. So the only other thing that I can do to get 4 is multiply 1 and 4. But if I add these, I get positive 5, so this needs to be negative and a negative. Right? If I make them both negative, they multiply to give me positive 4. Check. And then if I add them, if I add the two negatives together, I get negative 5. Check. All right. So then you just throw an x in front. Boom, boom. Throw another x in front of the other number, and you're done. That's it. That's all there is to it. All right, moving on. So then we have not classic factoring. I guess this would be like, I don't know what it would be called. It's like if you had classic Coke, then this one would be like just crack cocaine, I guess. Just kidding, that's horrible, don't do crack. Let's call this one, sometimes I call it extended factoring. Extended because it takes longer. Extended factoring. I was looking this up online because I was wondering what other people call this. And there's a couple different names for it. But basically this is just when A is not equal to 1. All right, so that's the fancy way for it. You might see this in a book. A is not equal to 1. What does that mean? Well, let me show you. I'm going to use my red for my recap. All right, so recap. Ax squared plus bx plus c. Whoa, so many letters. Okay, the A in front, if it's 1, then you just ignore it. There's nothing there. So this one, technically, there was an A in front. Right? So in this problem, there's technically a 1 there. All right, so I just ignore it. I just factor the 4. Just factor the 4 and then we're good. But if A is not 1, right? So for example, 2, oh, look at that, it's not 1. Oh, and by the way, A can also not equal 0, because if it was equal to 0, that'd be dumb, because then I wouldn't have an x squared term, and it would be really dumb to write 0x squared, right? Because it just cancels, it goes away. So obviously A is not equal to 0 either. All right, so 2x squared. Let's do a classic example here. So we'll do 5x plus 3. Literally just making this up as I go here. So what you do is 2 times 3, right? So 2 times 3, 2 times 3 gives you 6. Now I want to factor tree the 6. I want to factor tree what these two things, the 2 and the 3, right? Multiply them. Now I want to factor tree that and find out factors that give me 5. All right, so this is different and the same as this other one. Well, this other one, it was technically 1 times 4, right? And then you get factors of 4. So that's why we ignore it. Anything times 1 is just that number. So this case, it's 2 times 3, 2, put a little loopy on the 2, gives you 6. So we want factors of 6. Well, I mean, I literally just multiplied it, and now I'm going to break it up and put 2 and 3. Still didn't put that loopy on there. Because 2 plus 3 is 5. So there we go. That's what I want. Now, here's the trick. Right? So this is my trick method. There's 2 different ways to do extended factoring. Well, there's a bunch of different ways. So many ways. I might make a whole video on just doing this kind of factoring because there's just a million different ways you can do it. And I guarantee you, if you were to, if I were to poll like 1,000 random kids that are old enough to have taken this class, obviously, but not too old so that they forget it all. Then I'm sure they would be like, oh yeah, I learned it this way, I learned it that way. Like 10 minimum different ways that you could solve this. But anyways, this is the best way to do it, right? This is the only way, in my opinion, that you need to do this because it's a trick method, and I love trick methods. So here's the trick. It's called, let me give it a name because it's so cool. Super cool. We're going to call it 2 truths and a lie. Or I call it 1 truth and a lie. 1 truth, right? Like that game. 1 truth and 1 lie. Little markers on here to show that it's a 1 truth and 1 lie. All right, so it's kind of like the game, 2 truths and a lie. All right. So what we're going to do is we're going to make one of these a 2x and the other one an x? No, we're going to make it a 2x. What? But doesn't that multiply to give you 4x squared? Yes, it does. And that's the problem and the solution, right? So one of these is the truth and one of these is the lie. And we're going to find out which one. And our factors, by the way, we just found our factors, 2 and 3. Plus 2 plus 3. You put those factors in there just like you normally would. Now, which one's the truth? Which one's the lie? This one. This one can divide by 2. Therefore, it is a lie. It's lying. Right? So, it's a lie. This is a lie. Why is it a lie? Because this 2x squared plus 5x plus 3, you cannot do anything to take out a GCF, right? Remember step 1, the initial step 1, look for a GCF. None of these extra problems have had a GCF in them because I'm just focusing on this particular way to factor. So if there's no GCF, then there shouldn't be a GCF here, and there is. So this is lying. This is a liar. So we divide them by 2, divide by the GCF, and that's it. You don't factor it out. You just divide it. You just straight up divide it out. Right? So if I divide it, I get x plus 1. 2x over 2, that's x. 2 over 2 is 1. And this other guy was the truth. The truth will set you free. And that is your answer. I almost boxed it because I felt so proud of myself. Look at that. Okay. So there we go. Extended factoring. And then we've got the next thing here. Did I put a 2 on there? I did. Oh, so we're on C. We're on D. Sorry, C and D. All right. So then you have 4 or more terms. 4 or more terms. You could call it quadrinomial for 4. Right? Quadrinomial, pentanomial, hexanomial. I don't know. Just making it up now. I'm not even sure if that's what it's really called. 4 or more terms. So here I'm not really going to show too many examples because there's just so many things. So I'm just going to kind of write them out. And to save time, I think I'll just write them out like in a sentence here. I'll just type them. So here's what you could do. You could factor by grouping. Factor by grouping, and I'll make this bigger in a second. Factor by grouping. Actually, let me do that now. Factor by grouping. Defaults to Calibri. I don't even know what that means. 20. Is that big enough? It's not as big as I've been writing, though. Let's make it a little bigger. Let's do 26, because why not? All right, so factoring by grouping. Factor by grouping, which you can do typically with 4 terms. 4 terms is the most common example. All right, let me make this longer. There we go. So factoring by grouping is the most common example. And I'm going to go ahead and number these while I'm at it. Put a number on there. Okay, so factoring by grouping. 4 terms is the most common example, but you can have more. So it could be, you can have pretty much any composite. Oh, what's composite? Not prime. So basically any number that's not prime. Of course, we're not talking about fractions and decimals yet because those are nasty numbers and we don't like to talk about those. But 4, for instance, 4 is a composite number. It's the first composite number, actually. 4 or 6 or 8 or 9, those are composite numbers because I can multiply 2 or more prime numbers to get those numbers. All right, so any composite number of terms is what you would use. So any composite number of terms you can use to factor by grouping. All right. Then you have one of my favorites, synthetic division. And if you don't know what this is, it's okay because you probably have not taken this class yet. And I'm just handing out spoiler alerts right now. Right? And of course, synthetic division is sort of like a trick method. The long division And I don't mean like if I did 527 divided by 4, I don't mean that kind of long division. I mean long division of polynomials. Long division of polynomials. So you can factor by grouping, you can use synthetic division, you can use long division, etc. Right? There's probably a few other things in there, a few other methods that I didn't put in there. But yeah, so that's it. So if it has 4 or more terms, you're pretty much just going to look for factoring by grouping, synthetic division, long division, or some other term. Plug it into a graph, right? Use Desmos, right? Use the tools that you have, plug it in. Photomath, just kidding, that's cheating. But no, if you have like homework, whatever, I'm a total fan of Photomath for homework. I mean, unless it's graded, you know, if you're just practicing and you want to check the answer, then go for it. Use all the tools. All right? Real life, you can use all the tools. So use them all. All right? So this is everything here. This is everything. This is factoring. This is factoring.